Yes, thank you for the introduction. Welcome everybody back. Thanks to Barbara and Nicola for organizing this, and thanks really for doing it in person. I think that's really a fresh alternative to what we've done the last 1.5 years, even though faces can only half be seen. So we heard a lot about seismic tomography this morning, about seismic anisotropy, seismic attenuation, and I would like to give somewhat kind of laboratory mineral physics perspective to that, outlining what are the kind of key physical properties that we need to measure and still haven't measured to come up with a real kind of mineral physics reference data set that allows us to interpret all these seismic observables in a kind of coherent way in terms of the composition, the mineralogy, and the structure, also dynamics of the mantle. Yes. Before I start, I should briefly thank a few people who were involved, in particularly 3 PhD students who contributed significantly to what I'm going to show. Okay, so just a short introduction slide. So when it comes to what do we need to know from mineral physics to interpret these kind of images? So the kind of easiest thing we can think about from a mineral physics perspective is something like an isotropic seismic tomography model, either for compression or shear wave velocities, in which case, if it's all elastic, we only need the bulk modulus, the shear modulus, and the density, obviously as a function of pressure and temperature, and as for all the minerals that could potentially make up the Earth's mantle with all their chemical variability. But this is kind of the simplest case. It can become more complicated when you look at things like seismic anisotropy, as in this work here by Anna Ferreira. We need information about, as Jean-Paul Montagnier pointed out, about the elastic stiffness tensor components, or the elastic constants here in the kind of simplified notation of CIJs. And we need information about the crystallographic preferred orientation, the ways that crystals orient in a stress field. Now, this is already a lot more difficult from a kind of experimental perspective to measure, because these can be up to 21 components, so a lot more basically independent parameters than K and G. And the last thing, maybe there are other things, but the last major thing is something, if we want to interpret things like seismic attenuation, we have to look into time dependence of processes. And that is something, frequency or time dependence, and that is something that so far in the lab is really almost not been done, only for very upper mantle materials, but not for materials in the transitions of our lower mantle, for the vast majority of the mantle. Okay, so generally, maybe I should say this talk is outlined in a way that I will spend the first half about the first half just summarizing kind of the methods that we have, or that we're mostly using to measure these properties, and where we are today, and what are the major challenges and major gaps that exist. And then in the second part, I would like to introduce a kind of novel approach that we have been using since 1 or 2 years that allows us to at least, I think, tackle some of these and outline a few kind of future directions. This one is actually not working. Okay, so just this one slide. So how do we measure seismic wave velocities or elastic wave velocities in the laboratory? There are different techniques, but ultimately the vast majority of all the data we have come from 2 different types of experiments. One are so-called large volume press, sorry, too many ULVZs this morning, or multi-envelope press ultrasonics. So this is something where we have a big press, we have a sample of probably 1 millimeter size, and we propagate really physically an elastic wave through the sample at frequencies maybe around 1 megahertz. The big advantage of that is that high temperature is relatively routine for these kind of experiments. The major drawbacks is pressure is routinely limited to maybe 25 GPa. You might be able to go higher, but routine is really, 25 is actually already pretty high. So this is really just the top of the lower mantle. Is almost exclusively limited to polycrystalline samples, which means we get no information about the seismic anisotropy. We only get the average compression and shear wave velocities. And ideally, you need to couple that to a synchrotron, because it allows you to look at how long the sample is at high pressures, and because what you ultimately measure is a travel time. And if you don't know how long your sample is, you get wrong velocities. So that makes it complicated, because synchrotron beam time is limited, just in practical terms. The other major group of experiments are light scattering techniques in a diamond anvil cell. So a diamond anvil cell is a much smaller device. It allows us to go to much higher pressures, routinely the core metal boundary. And in this group, basically for two types of experiments, one is Brion scattering and one is impulsive stimulated light scattering. The principle, roughly speaking, is always that you focus a green laser in the sample that exchanges energy with the sound waves, with the acoustic phonons in the sample, and you measure that frequency shift and derive the sound waves. So the real advantage is here high pressure is possible and the galactic anisotropy can be measured. If you measure a single crystal, like one crystal, and you measure different directions, you can invert for the entire elastic tensor, all the CIJs. A big drawback is high temperature is difficult, just because diamonds don't like to be at high temperature, then they don't want to be diamonds anymore. So it's really difficult to do these things at high temperature, also because they take a lot of time to do. And time, again, favors all kind of chemical reactions, experimental problems at high temperatures. And you can measure polycrystalline samples, but the quality of these measurements is really not known. We don't know. These have been done, polycrystalline measurements have been done at high pressure, high temperature, just because it's easier than single crystal, but it's hard to really understand how good they are. And generally speaking, non-transparent samples are challenging, so most of these have been done on low iron content samples. So where are we with these kind of experiments when it comes to, this is a summary that focuses on the transition zone and the lower mantle, so the majority, volumetrically speaking, of the Earth's mantle. And it gives you in temperature and pressure space the maximum conditions that have been reached for the major mineral phases of the mantle, for single crystals as solid symbols and for polycrystals as open symbols. And obviously I'm not going to go into all the details of this, but I want to highlight a few things, and that is that we've measured a lot at high pressures, up to the pressure of the core metal boundary. We have measured things at high temperature, but at very limited pressures, and that's because these are done in the ultrasonics in the large volume press. And we have very, very little, almost no data in pressure temperature space, which is what we're interested in, obviously. The only data we have here are at really realistic mantle temperatures, are actually these 2 points, which are measured, as I said, alluded to before, on polycrystalline samples. So it's great that we can do these measurements. This is bridgemanite, this is actually MgO, so it's an iron-free periclase, if you like. But it's a little difficult to understand the quality of these. And okay, before I highlight a few more major gaps here, I'd just also like to add a positive note, and that is that the same diagram would have looked like this in 2017. So this is, 2017 has been basically chosen because that's where I started my PhD and started working on this. You can see it's almost blank, right? So we did do a lot of progress in these years, but we're still very short on anything in combined pressure temperature space. And then you have to keep in mind that often these are single studies on a single composition, right? So, you know, chemical variability and all of these things is really poorly known. So just to highlight a few things, post-perovskite has been only measured, there's one study that measured post-perovskite at kind of core metal boundary conditions on a polycrystalline sample, right? But post-perovskite is usually considered to be the cause for the double prime anisotropy, for which interpretation you would need the elastic constants. You need the anisotropy, which you cannot get from a polycrystalline measurement. Bridgemanite, there are two studies that reach kind of these pressures on single crystals. So if you want to interpret Anna Ferreira's data on the anisotropy in the top of a low mantle, I think, in terms of bridgemanite, these are the kind of data you need from an experimental point of view. They have been measured to 40 GPa on basically one sample with one composition, no temperature. The other point for bridgemanite is up here. This is a polycrystalline, I think, aluminium bearing sample, but no anisotropy information about this. And just the last thing I want to highlight is ferropericlase, just because ferropericlase, second most abundant mineral in the lower mantle, is in a way probably the easiest, or one of the easiest of these to measure, because it's cubic, it's relatively high symmetric from a crystallographic point of view, and it can be synthesized relatively easily in a laboratory. Ferropericlase has been measured to very high pressures as a single crystal. It has been measured well, this is MgO, so this is without iron, and why that's important, we'll come to that in a minute, at kind of realistic mantle pressures and temperatures, but as a polycrystal. And this is the only point in combined, or in simultaneous pressure temperature space that gives you the elastic anisotropy. And that's also the highest one on an iron-bearing sample. Why is that important? Because ferropericlase undergoes, or the iron in ferropericlase changes its spin state somewhere here, and that affects the elastic properties. So that means that while this one covers this effect, this one doesn't because it's happening somewhere here, and this one doesn't because it doesn't contain iron. Okay, so there are several limitations in the data set we have. And does that matter is the question, obviously. It matters because it leads to a complete ambiguity in interpreting observations, seismic observations in the lower mantle. This is just a kind of cartoon-like depiction of major things, features that have been depicted in the lower mantle by various seismic tomography studies. And the numbers here, for instance, here or here or here, refer to a mineral physics-based interpretation of these. And without going into details of this, you immediately see that most of these features, associated with different numbers or different letters, which means different causes have been proposed. So there's a big ambiguity in this, and this is at least to some extent because we just don't know the physical properties well enough at these conditions to unravel the causes. So just to pick out a few things, for instance, seismic scatterers in the mid-mantle here have been assigned to composition, that's the X here, to changes in the spin state of the material, so the electronic state basically, to a phase transition in stishovite, SiO2, or to a phase transition in calcium silicate perovskite. The double prime anisotropy here has been assigned to post-perovskite alignment, ferropericlase alignment, or the alignment of melt in a shape-preferred fashion, where you have these melt pockets aligned. And the same for the origin of large low velocity provinces, can be temperature, composition, cubic calcium silicate perovskite, post-perovskite, and there are probably more, right? So we just don't have enough information to really unravel causes. And I just tried to summarize the main challenges here, and I put some in a green box and some in a red box. This is kind of to indicate which ones I think can be solved in principle by the methodology we have in the lab right now. And the others, the red ones, are the ones that need technological developments to be really fully addressed. So these ones can be done. You can measure systematic variations with chemistry. You've seen in the previous works, or the summary basically, that we can achieve pressure temperature conditions of the lower mantle, but we have to do it, so it just takes a lot of manpower. And the same for understanding measurements on polycrystals and to get some statistics so that we don't have to rely on a single study. For instance, of Bridgmanite, there is basically one really single study for the elastic properties of a single crystal. The red ones are a little more tricky. They can only partially be done now, and these are high temperature measurements in the diamond amber cell. I showed some, but there is really the main problem that we cannot contain high temperatures for a sufficiently long time to measure meaningful things often. And then things like the time dependence of processes that can then be related to attenuation. So usually we measure at super high frequencies, gigahertz frequencies or megahertz frequencies, far away from seismic frequencies. So the question is that relevant for seismic frequencies, or are there other processes that we have to take into account? And both of these actually strongly relate to the understanding of phase transitions in the mantle. Some of these I've depicted as numbers on the previous slides. Okay, so there's a lot to do. And I would like to spend the remaining minutes of this talk to outline a kind of novel approach that we have used that can tackle some of these. I'm not saying it can tackle all of these, but it will help us to approach some of these. And I would like to outline this using the example of the iron spin crossover that I've mentioned a few times before. So the iron spin crossover is this electronic change in ferropericlase in the ferrous iron that is contained in ferropericlase, where it changes from a so-called high spin to a low spin state, so the electrons, the outer electrons, pair in low-lying orbitals. Now, the details are not so important. What is important that this doesn't happen instantaneously. It happens in the mid-mantle, but it doesn't happen instantaneously. It happens over a certain depth range. And in that range where it happens, there is a so-called mixed spin state, so where some of the iron are high spin and some are low spin state. And in this mixed spin state, physical properties are really different, from the high spin and the low spin state. In particular, the bulk modulus softens by about 50%, viscosity decreases, we don't know quite how much, but maybe by a factor of 10 or 100, and then there are changes in transport properties, maybe also iron partitioning. Just to outline a few things, so early measurements showed that because the bulk modulus softens, and bulk modulus is part of the compression wave velocity equation, you can see this dip in compression wave velocities. This is at 300 Kelvin. Shear velocities don't show any change. Spin transitions happening here. And at that time, this is a long time ago, we modeled how temperature would affect that. And it was known that temperature would broaden it, but quantitatively, this is a bit, still actually not quite understood. But the interesting bit is you can get parts of the mantle, for instance, where compression wave velocities are not really dependent on temperature at all, right? They're really insensitive, or they're inversely related to temperature. So the ratio of VP to VS actually might be quite strongly perturbed by this. And this idea was basically used later to argue that things like plumes could potentially be invisible in seismic P wave tomography in the mid-mantle, just because velocities are not sensitive to temperature, which you would usually expect. And it might also have effects on viscosity, could accelerate slabs to the core mantle boundary, but I'm going to go into this in detail. But the important bit is we need to understand where actually this happens in the mantle and how it affects the bulk modulus. And from an experimental point of view, this is not so clear. So this is bulk modulus as a function of pressure for the only 2 experimental studies that exist, basically. And they both have very similar iron contents. It shows that bulk modulus goes up with pressure, and then it shows this dip when it goes through the spin transition. But in terms of the widths and the kind of magnitude, they are not quite in much agreement as we would like them to be, given that they are really close in iron content. So the question is why? Now, these are light scattering studies, and I think I mentioned before that these are very time consuming, so it probably took months to get these data. So it's nothing where you would just do 100 measurements and then compare them. You have this poor agreement. They are limited to low iron contents because these samples need to be transparent to laser light, and there is no single high temperature measurement of this effect, right? This is all 300 Kelvin. So an alternative way to get the bulk modulus is actually from a curve like this, which is a standard experiment that mineral physics do, measuring the unit cell volume as a function of pressure. And unit cell volume obviously goes down with pressure, and the spin transition should have a signature here, so it should lead to an additional decrease in volume. But this is a typical data set that people collected, and it's very difficult, both in the blue and in the orange data, to see this signature. It might be there, it might not be there. Pressure resolution is not great, and there is a bit of scatter in the data. So what we did is we used a kind of new approach here. It's similar to that, but the novelty here is that we use a so-called dynamic diamond anvil cell. That's a diamond anvil cell that is driven by a piezoelectric actuator. So usually, when we increase pressure in the diamond anvil cell, we either use screws or we use a gas membrane. And this one is driven by a piezoelectric actuator. The advantage is that the compression is very smooth and that we can tailor the compression path and the speed. And we combine that with a time-resolved X-ray diffraction. So these are novel detectors that allow us to quickly measure the unit cell volume, so that basically we make a movie of the compression instead of having individual data points. So what we get is data that look like this. So the black one here are data we collected. And this is not a fitting curve. This is kind of individual images or individual data points stacked together. So I think these are 1,000 individual images. And this looks quite a bit different. Yes. Thanks. From the previous data sets that we could previously collect, right? And the whole experiment only takes a few, in this case, minutes, I think, but could also be seconds. So it's very, very fast compared to these light scattering studies. Now, what do you see here? You can see actually the spin transition happening here. And you can now really take the thermodynamic definition of the bulk modulus, which is dp/dv, and apply that to this curve and directly calculate the bulk modulus from this definition. If you try to apply it to this curve, I mean, I think you can immediately see that the derivative would give you kind of crazy behavior. But here you can immediately see it, okay? So the gray points here is what we get from these kind of data. This is bulk modulus as a function of pressure. Now this has been measured for ferropericlase with 20% iron, so it's kind of a realistic. So we expect ferropericlase in the mantle to have maybe 15 or 20% iron, more than the 6% or 8% that previous studies measured. And you can nicely see this softening here. It's actually a bit broader than maybe expected. We also, in collaboration with Stephen Stackhouse, we added a bit of theory here to kind of, find out the microscopic reasons why we see this broad softening. I'm not going to go into the details of this, but these new data are quite a bit different from the previous theory. That's a bit hard to see here, but plots somewhere here. Now, these are interesting results because it's like the first measurement on a realistic iron content, but even more so, I think, because this is a fast experiment. So that allows us to do these measurements in a wide range of pressure, temperature, and composition space. So we can very quickly do this for different iron contents, and we can do it at high temperature because we only need to keep the cell at high temperature for a few minutes. And we started doing that, so this is basically what we get for the bulk modulus softening at 1000 Kelvin, the red symbols here. There's a bit of a weird feature here, which we still don't quite understand, but you can see the softening very clearly, and again, it's at least to first order very consistent with the theory, and it's also very nicely in agreement with the only high temperature measurements that exist of the bulk modulus that stop somewhere here, right, before the spin transition. So if you extrapolate that, we're pretty much there. There's a bit of scatter, it's not perfect, but it is the first ever high temperature measurement of this bulk modulus softening. And together with the theory, actually, this allows us to come up with our idea of how the spin state changes throughout the mantle, which is summarized here. This is temperature, this is pressure. So everywhere here, ferropericlase is in high spin state, everywhere here it's in low spin state, and everywhere in this kind of rainbow color region here, it's in mixed spin state. And this is a typical geotherm. So if you follow the spin state along this geotherm, which is also shown here as a low spin fraction, you see that actually for the majority of the mantle, ferropericlase is in this mixed spin state. So it's not high spin, it's not low spin, it's in the mixed spin, which is where the bulk modulus is softened, where the viscosity is decreased, where the transport properties are affected. So this is actually quite interesting result. And there was a lot of debate about this before with a lot of different predictions. Okay, so the last 2 minutes, is that right about? Okay. I would just like to outline some future directions that we can take with this piezoelectric-driven diamond amber cell, the so-called DDAC, because this piezo actuator does not only allow us to compress the sample, but also allow us to cycle stress or pressure on the sample. So what we can do is we can go, this is schematically shown here, go to target pressure and basically modulate stress at this average pressure with a given frequency and a given amplitude. So this is going a little bit in the direction of simulating a seismic wave that propagates through the sample, right? It's not quite a seismic wave, it's a stress oscillation, but it's going in the direction. And we can do that with a seismic frequency. So it's not gigahertz, not megahertz, this is 1 hertz. And in this kind of proof of concept study, we cycled with 1 hertz. You can see this is pressure going up and down. And at the same time, this is the sample unit cell volume, basically reacting to that pressure change. You have the largest volume where the pressure is the lowest because it's less stressed. And we applied that in this kind of first proof of concept work again to ferropericlase just to see if you can see this bulk modulus softening here as well, because from these data you can directly derive the bulk modulus. But now this is the bulk modulus in a way effective at 1 hertz, right? If it doesn't soften at this frequency because the process is too slow, it wouldn't soften. But the spin transition is a very fast process, so we expected it to happen. But this will allow us in the future, we extended that to high temperature now, so this is cycling at core metal boundary pressures and 1400 Kelvin. So this is something that will hopefully allow us to look into the time or frequency dependence of processes. Maybe just as a last thing, this one is an example where we cycle pressure, where NaCl, sodium chloride, undergoes the B1, B2 phase transitions. It's just some phase transition where it goes from a so-called B1 to B2 phase. And this curve here gives you a feeling of how much of the B2 phase we have. So whenever we increase pressure, while the average pressure actually stays constant, we get more of the new phase. So this is something in the direction of coupling of this stress oscillations to phase transition. Okay, so this is basically the summary slide, so I hope that...
Oh, sorry. You're done.
Okay, yeah, I'm done. So I hope we can solve a lot of this with the new approach and other approaches in the future, and I just want to kind of advertise this new edu book before.
Thank you.